All right, welcome to part 3 of our 7-part series on chapter 2. Today we're going to talk about true stress and strain and talk a little bit about stress or strain coefficients and strain hardening. So remember, the engineering stress was based on the original cross-sectional area A0. Well, this is not necessarily a perfect approximation of what's going on as you're stretching the material or as you're applying stress and resulting in strain in the material. The cross-sectional area will actually start to change as the material is being strained. So true stress and strain is written as sigma equals the load divided by the instantaneous cross-sectional area. So that's the area of the cross-section of the generally cylinder you're pulling on. And it doesn't have to be a cylindrical cross-section. It could be a rectangular cross-section if you're doing a sample that's a dog bone shape rather than the cylindrical shape. Okay. So as we're getting longer and thinner as we're pulling on this thing, we start to get necking, and we mentioned that earlier in previous lectures. And that necking is a reduction in the cross-sectional area. So the true cross-sectional area is not constant throughout the process. Okay, so true stress is the ratio of the load over the instantaneous cross-sectional area. So this is true stress. Remember, engineering stress has this little 0 in here, which is the original cross-sectional area. Okay, so now we talked about the true stress and the cross-sectional area, the instantaneous cross-sectional area. If you really want to get into being correct or exact, you have to talk about true strain. So true strain is related to the instantaneous change in the length divided by the overall length. Okay, so at any point in time as you're pulling on your sample or as your sample is being stressed, right, the strain is changing as well, and there's an instantaneous change in the strain as a function of whatever length you're at during the process. So in order to determine that, you have to take the integral. So it's the change in length divided by the overall length as you go from the starting length to the ending length. So here's the starting length. This is the length that you finish at wherever you are in the process, and this is delta L over L. So you just do an integral. So if you remember from calculus, the result of this integral, okay, is given here. All right, so you take the integral of 1 over x dx, it equals the natural log of x, okay, plus a constant. Well, if you put in the constant, right, that's your L naught. So you get something like natural log of L minus the natural log of L naught, right? And you can combine that into the natural log of L over L naught. So this is just basic math that you should have had in calc. If you don't understand how to do this integral, I suggest you review that. And you can also go to the Khan Academy and take a look at integrating 1 over x dx. Okay, so you might say, well, what difference does it make? True stress and strain versus true or engineering stress and strain. Who cares? Well, let's take a look at strain. So we can put in some numbers to get a comparison between the two. So if the engineering strain, E, is equal to 0.1, right? What is epsilon, which is the true strain? So you can just put in some numbers into these two equations and see what the result is. So if this is 0.1, that means this here, the L minus L naught, so what you end up with minus what you start with in terms of length, okay, divided by the original length is equal to 0.1 means I stretched it by 10%. Okay, so you would say, okay, what numbers do I have to put in to do that? Right, so let's say you use 1 as L naught. So what divided by 1 will give you 0.1. Okay, so 0.1 will. So if you stretch it by 10% or 1.1 of L naught and divide by 1, you're going to get 0.1. So if you take those numbers and you throw it into the true strain equation, okay, you're going to get something that looks like 0.095. So when the engineering strain is 0.1, the true strain is 0.095. So it's a very small difference, okay? So they're relatively close. So in the case of very small strains, you can use the two interchangeably and get very close results in your calculations. But what happens if we double the length, right? That means we put a 2 in for L and a 1 in for L naught, right? 2 minus 1 divided by 1 is equal to 1. So if our engineering strain is 1, what's our true strain going to be? Well, putting in the same numbers, you're going to get 0.69. So make sure you try it with a bunch of different numbers and be able to compare the two. This may be on a test, a quiz question, whatnot. So, you know, get an understanding of that. So you can see as the more you stretch something, the more strain you put a material under, the bigger the difference between engineering strain and true strain becomes. All right, so here's some really cool graphs. On the left side, you see the load as a function of extension. So this is basically what your tensile testing widget is measuring, right? So you put your sample, so you put your cylinder sample, right? Oops, in your tensile tester, and you put a load on it, right? You pull on it by P. Okay. So now you're going to be stretching this thing. So this is what the machine sees, right? A certain load, P. And the machine's going to measure the extension, right? So you start with L naught, and then you finish later with an L, and that's your delta L, L minus L naught, right here. Okay? So that's what the machine sees. So the machine will start to plot this. As it's pulling on it, then it starts to neck, comes down, and it finally breaks. Okay, so that's what the machine sees. And when it breaks, the load goes to 0 because there's nothing holding it back. Okay? All right, so on the right side graph, it's the same curve essentially. Okay? And what we're looking at here is the stress. Okay, so that's load over what? Ooh. A naught. Okay. The original cross-sectional area. And the strain is your delta L over L naught. Okay? And you get the same curve. So why would you care if you use this one here or this one here? Well, if you're comparing different materials, you're going to get different curves, naturally. But you have to be able to compare apples to apples. So if you divide by A naught, right, and you look at the unitless strain as you're pulling on this thing, pardon my dog's barking, I don't know if you can hear that. You can pull on those two different samples. So you have two different materials and you're trying to compare them. You have to normalize the data. You have to calibrate the data to the sample cross-sectional area. Okay, so if you have aluminum and steel and maybe they're slightly different diameters, you're going to get different load and extension curves, and you can't really know if it's the sample dimensions that cause the differences or if it's the material itself, if you're going to do load versus extension. So that's why we do stress versus strain. It gets rid of the geometrical components or attributes to the stress or the load extension data that you get. Okay, so you're calibrating for the sample size, the sample geometry, and that sort of thing. So that's why we do stress strain. So here we have another stress strain set of curves. So on the right is your standard engineering stress strain. Okay, and on the left is your true stress strain. Okay, true stress versus true strain. And this is basically the same material on the right and on the left. It's just two different ways of plotting the data. Okay, and you can see what's happening here, right? You're pulling on the sample, right? So it's getting longer. Okay, so the true strain is increasing, so it's getting longer as you pull on it, and then it curves over. Okay, and then it finally breaks. Okay, notice how it's constantly going up. So think about that. As the area is shrinking and your load is increasing to continue the stretching, right? That value you're going to get for the true stress is going to continue increasing as you pull on this thing. Now, think about it, if you're pulling on taffy, it's really hard to pull for a while, really hard to pull, really hard to pull, and then you get to a point where it's easy to pull, right? So that's your load that you're pulling on the taffy. But if you look at the cross-sectional area of the taffy as you're pulling on it, the stress is actually increasing because the area is shrinking for the same load. So your P being load over area, that P over area ratio is going up faster than the P over A naught ratio would go up. Okay, so that's why this stress keeps going up. Okay, and on the right side it doesn't, because we're not accounting for the instantaneous cross-sectional area. Okay, make sure you understand the differences between these two curves here and be able to articulate what's different about it and why it's different and why you would use one over the other. All right, so this might be a good time to pause the video and look at it and sketch a few curves out and try to figure out what's going on and that sort of thing. Okay, so this slide is about what's this corrected for necking necking part of the curve. What does that mean? Right? You're like, well, okay, I get that it keeps going up because the cross-sectional area is getting smaller. So load over area, that number, that's the true stress at any given point along the stretching. That true stress is going up because my area is going smaller, so I get that. But if I correct for necking, why would that load, that stress, actually reduce? Well, what this is trying to compensate for is the longitudinal stress. So the longitudinal is the up and down, right? Stress. So if I'm going to go ahead and sketch in here. Here's my original sample. Okay, I'm going to try to switch colors here, and maybe we can elucidate a little bit what goes on. So as it gets longer, right, it's going to get thinner. So let me just try to show. I'm not very good at drawing with a mouse, so pardon me. And then you get some necking. Okay, and this also got a little bit longer. Okay, you got to conserve volume. This is not to scale, so I apologize for that. So it's gotten longer. We've pulled on it for a bit with some sort of load. Okay, P. So we pulled on it with some kind of load P, and it starts to neck. Well, what's causing it to stretch? First of all, it's the load in the longitudinal direction, which is up and down. So you got a force, right, pulling it, and you can flip it around, and it doesn't matter. You're pulling it in the longitudinal direction, so that's why it's getting longer. But you've got to have some force that's lateral, right? You got to have a force that's causing it to neck, to shrink down, And the forces, you can't just create forces out of nothing. It's got to come from somewhere. So, your machine's telling you, I'm pulling on it with some force. Let's label it 1. Okay, so it's pulling on it, and that's what the machine sees. But some of that energy is going to be transferred laterally. So the actual force on the material itself is the longitudinal force. Let's call it PL instead, right? Actually, the longitudinal force is equal to the force of the machine, which we call P1, okay, minus the lateral forces, LAT. Okay, so some of the force, that's used by the machine, right? That's pulling on the sample. Some of that force is transferred into the lateral force. So the actual load in the z direction in the material, the load in the z direction in the material is this corrected for necking. Okay? So that's actually what's happening on the material side of the house, right? Within the material itself. So you got to kind of think about it, shrink yourself down, walk around inside the sample, be the sample. You're feeling a force pulling you up, stretching you, right? And then at the same time, you're feeling forces around your waist that's kind of pulling you in because, that mass that's being stretched up has to come from somewhere when it starts to neck. So it's got to collapse on itself. So there has to be some sort of lateral force causing that collapse in the lateral direction, which is perpendicular to the z-axis. So in x and y, you've got forces coming in. It's actually a radial force, right? It goes all the way around. All right, and that's what this corrected for necking is. So I want you to, pause here if you need to and take a look at this this slide and go through it in your own head and draw a picture of the sample, hopefully better than my picture here. And then you'll be able to understand exactly what's going on and what the corrected for necking means. Okay, so now we've got the corrected for necking version of true stress versus true strain. Okay, if we take our true stress versus true strain graph and plot it on a log-log scale, that's what the difference between these two are, right? Take a look at the scale here, right? It goes in decades rather than linear, right? And the same thing with the stress. So strains in a log scale and stresses in a log scale. If I were to plot this data on the right, on the left side, you would get a straight line. And that's what's really cool about engineering and physics and stuff. A lot of things are related in a log fashion, like a cooling curve, right? If you measure the temperature versus time, you have a hot cup of tea, and then you have, the equilibrium temperature is room temperature. If you were to measure that temperature over time, it would be an exponential decay. And if you put it on a log linear scale, it would be a straight line. So logarithmic functions are natural, right? Radioactivity is the same way. Cooling, energy diffusion, those kind of things are all kind of on a logarithmic scale. So are lots of material properties. So if we plot true stress versus true strain on a log scale, we get a straight line. So that's pretty cool. So whenever you get a straight line, you think of what? Y equals mx plus b. Okay, and I don't know if they still use mx plus b in basic trig and algebra. I think I learned this stuff either in mid school or high school. M is the slope, rise over run. All right, that was drilled into my head. I hope it was drilled into yours. And then B is what? Is the intercept, right? So you see this y equals, excuse me, you see this y equals mx plus b relationship, but it's on a log scale. So you can look at the slope as being some sort of material property, right? Different materials are going to have a different slope, and that's what n represents in this graphic. Okay? And so that's pretty interesting. And also look at where it starts. It starts at 0.1. 0.01, excuse me. Okay? So that's typically when you start to get into the plastic region. Okay? Right around 1 or 2%. If you remember the engineering stress and strain curves we talked about earlier, the true stress and strain curves, right, are straight at about 1 or 2%. Okay? So if we were to go to 0, you'd probably see something that comes almost straight up, very high slope, and then it bends over and when it gets into that plastic region. And then it finally breaks. This is where it breaks. Okay, so you can look at this and say, oh, when it gets twice the length, it breaks. That's another thing you can see from this graphic. Okay, so we've got rise over run. To find out what n is, we've got this here where it crosses the y-axis. Right, so you can find m and n from these curves. So let's talk about it a little bit more. Okay, so this is the answer to the previous question, which says it's log-log versus linear. Okay, why do we start at 0.01? Because that's when L is equal to 1.01 L naught. So it's elongated by about 1% from the original, typically after the yield stress point and when strain hardening begins. So after about 1% or so of stretching this material, you start to get out of the elastic region and into the region where you yield, and you start getting plastic deformation and also what's called strain hardening. So this graph is used to study strain hardening. Okay, so like I said, we have a straight line curve. So that being a straight line, we can say, okay, true stress, that's this y-axis here, okay. E to the n, that ends up being the slope here, and k is what's called the strength coefficient. All right, so how do we determine those things? Okay, well, first let's take a look at the units. What units is K? What is the strength coefficient? First off, what unit is it? Okay, well, E, remember E, elongation, true strain, that's a unitless number, right? It's the log of L over L naught. All right, so that's unitless. So a unitless raised to a unitless number is still unitless. So K is going to take on the units of what true stresses. Okay. So take a look at this. Is it going to be kilograms per meter squared, or is it going to be megapascals of pressure unit? Think about it. You can pause it. Well, it's a pressure unit. Okay. All right. So let's say, okay, what is K in PSI? All right, pounds per square inch. That's what this is here. That's a pressure unit. So how do we find K? Okay, it's 180 times 10 to the third. So how did we find that? Right, K is a constant. So we want to find a number, this, where it equals 1. If this equals 1, e to the n, epsilon to the n, I should say, when epsilon raised to the n power, we don't know what n is yet, right? But when it's raised to the n power, you're going to get a 1, right? So when this becomes a 1, then K is going to be equal to your stress at that point. So when true strain, epsilon, okay, is equal to 1 raised to any power, so 1 to whatever power you want, right? 1 to the n is equal to 1. Okay, so you go, oh, this is where epsilon is 1. If we come straight up, we look here, and then we cross over. That's the stress at which E epsilon is equal to 1. Okay, so this term, you can, 1 times K is K. This term becomes not important for finding K. So now you got to be able to interpret a logarithmic graph. So remember, this would be like 20, right? And then this here would be 30, 40, 50. I'm not drawing it to scale very well, but they get closer and closer together, right, on a log scale. So if you look at this carefully, this is right around 180 or so, maybe 200. Some people may say 200. The closest one in these answers is at 180. All right, so there you go. So how do we find n? What's the trick to finding n? That's the slope. That's rise over run. So what we can do is we can take a look at maybe 2 points. Okay, find out the run, find out the rise. So you find out, the difference between this and this. That's the rise. This would be your rise. Okay, and then this would be your run. So you might be able to eyeball it and pick the best answer out of these. So I'll give you a couple of seconds. The hint here is to take the log of these things, right? And then look at that. So there you go. If you take the log of 180 minus the log of 50, so why is it 50? Well, we're guessing this is 50 here. This is 180 from before. So take the log of those two numbers and divide by the log of these two numbers here and here, which is this number. Okay, so it's a log of 1 minus the log of 0.02. That gives you 33. And to test it out, you can put a 0.33, not 33, it's 0.33. You can put a 0.33 in for n, right, and test it out, okay, at let's say 0.1, and see if you get the right true stress. Okay, so why do we go through all of these hoop jumpings? Who cares, right? Well, you can classify different materials by their strength coefficients and their strain hardening exponent, right? The strain hardening exponent, which is this N, strain hardening exponent. Okay, strain coefficient, or strength coefficient K. So different materials will have different values. But once you know those values, you can model it in something like SolidWorks. That's kind of how SolidWorks works, right? You have all of these material property parameters that it knows that it's collected over time, or you provide those or change those because you have a different material or a different version of the material, and you've done testing with tensile testers and things like that to come up with the new numbers. And then you put them into your finite element analysis, and then it gives you a simulation of what's going on, and you can predict how that material is going to behave, if it's part of a strut in an airplane wing, or if it's holding up a bridge, or if it's a rebar bar inside a concrete, and you're doing, you know, some kind of civil engineering work. You know, all of those kind of things. It all comes back to basic material property testing. And that's why we do tensile testing and we do hardness testing and all of those things, okay? Is so that you can model it. That's really the whole reason for it. You can model it, design something, and feel confident that what you're going to build is going to work. And it's going to have several factors of safety, and you're not going to kill people. Like they step on the ladder and it collapses, right? All right, so here's a table of the typical values for K and N for selected metals. Okay, so if we take a look at it and say, okay, our previous example, can we guess what kind of material it is? So we have a strength coefficient of 180 times 10 to the third psi, or 180 kilo psi. You know, and you go, well, I can't find it here because it's in megapascals. Well, if you do the conversion of 180 times 10 to the third into megapascals, you'll get something close to 1,200 megapascals. Okay, so if we go look at this on the chart, you know, you can start looking for areas where you get about 1,200 megapascals. So you've got something here along those lines. And then you could argue maybe something along here as well. And then you start looking at the ends, right? The strain hardening exponents. Well, this is kind of close, right? This is kind of close. This is a little low. This one, you could argue maybe this point as well. So maybe it's this material here, or it could be some of this one version of steel. So you can make an argument it's titanium, or it could be a steel. And even this cobalt one here, it's a little bit too high, right? So you could argue the point. But anyway, you get the idea there, right? So, you know, it's probably somewhere in the range of some of the steels. All right, so now if we go look at these true stress strain curves, and we look at them in detail, and we put a whole bunch of materials on there, similar to the materials we saw in the previous table, you can start to see how these compare to each other. Okay, so some things to look at or to notice here, we don't really have an elastic part, right? The elastic part isn't really shown. Okay, so it goes back to that other discussion we had a little bit earlier. So the way this is graphed, where this curve, for example, here, this 4130 steel, this would be the yield strength right here. Okay, and then when it starts to bend, that's the part of the regular stress strain curve, right? How it comes up, it goes over. This is the engineering stress strain. It comes back down and then it breaks. Remember the linear thing? And it's the load divided by the original cross-sectional area, and then the engineering strain, which is L minus L naught over L naught, not the logarithmic version of that. So when you compare that, this up here is the ultimate tensile strength at the peak. Okay, that corresponds to where these things start to bend over. Okay, so that would be the UTS. All right, and then where the curve ends, well, that's where it broke. That's called the fracture strength. Okay, so if you come across here, oops, that would be the fracture strength for the brass. Okay, you just come straight across on the stainless steel. That's the fracture strength right here. Okay, of the stainless steel. So you should probably review engineering stress and strain versus true stress and strain. Here's a graph which shows both of them on top of each other. The red curve is the engineering stress and strain, and the blue curve would be the true stress and strain. Okay, and they've kind of been normalized. So you can see it's a very sharp elastic region, and then it starts to, right when it yields, it starts to be looking like this for the engineering stress and strain. And then the true stress and strain takes into account the cross-sectional area getting smaller. Okay, and the true strain takes into account the instantaneous strain as a function of L. So that gives you this blue curve here, okay, which I'm coloring red right now. All right, so that's an overlap. And, this is a nice little graphic here. Region 5 is the necking region, right? Region 4 is strain hardening. Okay. 3 is where it ruptures or breaks. 2 is the yield strength, where it begins to yield. That's an important material property. And the ultimate strength, ultimate tensile strength, is 1. So you can find that in the engineering stress strain curve. It's kind of hard to find on the true stress and true strain curve. Okay. So, and that was it for this lecture. So the next one's going to be part 4. Okay, so what do these true stress and strain curves tell us? Thank you.